So now I will do a couple of problems that will hopefully help you understand the concepts of span, linear dependence, and linear independence. So consider, I'm going to imagine the case, a simple case, where we only have 3 vectors, okay? v1, v2, and v3. So if I ask you to calculate the span of these 3 vectors, you know that several things can happen. So either the vectors are linearly independent, which means that they are all pointing in different directions, and they span a 3-dimensional space. Yeah. So you could say that 2 of them are in a plane, and the third one is outside of that plane. Or maybe the 3 of them are in a plane, in the same plane. And this means that they are not linearly independent, and they would span a 2-dimensional space. Or maybe 2 of them are parallel, one parallel to the other, like here, v1 parallel to v2. And v3, therefore, is not enough to provide 3 degrees of freedom, three dimensions. So the span is still 2 dimensions. Yeah. Or maybe the 3 of them are all parallel to each other, and then they only span a 1-dimensional line. So how does this look like in an actual problem, when I give you 3 actual vectors with numbers? Yeah. So that's this problem, problem 1. Check the linear independence of vectors v1, v2, and v3, and I provide you the numbers for these 3 vectors. So let's check the linear independence or the linear dependence of these vectors. So how do we do it? So remember, to check for linear dependence, we need to check if we can have a linear combination equal to 0 or not. So this is the question. So if the only value that achieves this is to have all the AIs equal to 0, then they are linearly independent. But if there is some solution in which AI is not all zeros, then it means that the vectors are linearly dependent. So how do we find this out? Well, we just write it down. So what does this equation mean? It means that A1 times V1 plus A2 times V2 plus A3 times V3 is equal to 0, 0, 0. That's how the equation looks like. Yeah. Or we could actually substitute the actual vectors. So A1 times the first vector, which is 1, 1, 0, plus A2 times the second vector, which is 1, 0, 1, plus A3 times the third vector, which is 0, 1, 1, equals 0, 0, 0. So now the left-hand side is a vector, right? So which vector is it? So it would be A1 plus A2 as the first component. It would be A1 plus A3 as the second component, and it would be A2 plus A3 as the third component when you do this scalar multiplication and addition of vectors. And this must be equal to 0, 0, 0. So what this means is that this is actually a system of 3 equations. So we have 3 equations. A1 plus A2 equals 0, A1 plus A3 equals 0, and A2 plus A3 equals 0. So let's label these equations as 1, 2, and 3. So now we need to find the solutions to this system. If the only solution is that A1 equals A2 equals A3 equals 0, which is a trivial solution, that solution is always true. If that's the only solution, then the vectors are linearly independent. Okay, so let's find out. So one way to solve this simultaneous system of equations is to do 1 minus 2. So equation 1 minus equation 2, and then we get A1 minus A1 goes to 0, A2 minus A3 equals 0. And therefore this means that A2 equals A3. Okay, but now if we substitute that result into the third equation, which says that A2 plus A3 equals 0, what we get is that, so A2 plus A3 equals 0, we substitute in this condition here, and what we get is that 2A2 equals 0, which means that A2 equals 0. And using the condition that we found above, it means that A3 is also equal to 0. Okay, now what about A1? Okay, we can substitute those two results into 1. So equation 1 says that A1 plus A2 equals 0, but if A2 equals 0, this means that A1 equals 0. So there you have it. We found a solution in which A1 equals A2 equals A3 equals 0. They all equal 0, and that's the only way to make this statement true. And therefore, this is exactly the definition of being linearly independent. This means that these three vectors look like this. Yeah, so they are spanning a three-dimensional space. They are not, the three of them are not contained in the same plane. Quite interesting, right? That solving a system of equations, we can find out whether three vectors are in the same plane or not. Now consider this other example. It's the same problem, but with three different vectors, okay? So, again, we follow the same steps. We want to check whether the linear combination of the vectors equals to 0 or not. So we want to check that. So we write down the equations. So A1 times V1 plus A2 times V2 plus A3 times V3 equals 0. And we substitute the vectors, and we get that A1 and the first vector is given by 0 minus 1, 1. Plus A2 times vector 0, 1, minus 1. Plus A3 times the vector 0, 1, 2. And this is equal to 0, 0, 0, vector 0. So this means that we have actually three equations, the same as before. And what are the three equations? They are 0 equals 0, that's the top equation, right? Because we have 0 times A1 plus 0 times A2 plus 0 times A3. So the left-hand side is 0 equals 0. Then the next one is minus A1 plus A2 plus A3 equals 0. And then the third equation is A1 minus A2 plus 2A3 equals 0. I just developed the vectors multiplied by A1, A2, or A3 and then added them up. Okay, so we have these three equations. So we could call them 1, 2, and 3, right? So obviously the first equation is not giving us any information, but we can still solve for the other two. So for example, we can do 2 plus 3. So equation 2 plus equation 3. And what do we get? So if you add up, you can see that the A1s and the A2s will cancel out, right? Because we have plus and minus and then plus and minus. So what we will get is that 3A3 equals 0, which means that A3 equals 0. So we found that the solution must always have A3 equals 0. But now we substitute this solution into the other two. Okay. So now equations 2 and 3, how do they end up looking once you substitute A3 equals 0? So they look like this. Minus A1 plus A2 equals 0, and A1 minus A2 equals 0. Of course, if you look at this, these two equations are actually the same equation. They give you the same information because it's just multiplying by minus 1 on both sides. So they are the same equation. So the solution in general to this equation is that A1 is equal to A2. And by having this solution, that would be enough. That would enable us to get a total vector that is equal to 0. And it doesn't need A1 and A2 to be 0. Therefore, there is a solution that is not the trivial solution to this total system. So if you don't believe me, let's check. Let's say, for example, and this is just an example. Let's say that A1 equals A2 equals 1, while A3 equals 0. So what happens when we do the linear combination of the three vectors? We do a1 times the first vector would be 1 times the first vector, plus a2, which is again 1 times the second vector, which is 0, 1, minus 1, and then plus a3, which is 0 times the third vector, 0, 1, 2. And what do we get? We get 0, 0, 0. So indeed we have combined the first two vectors and the result can be 0 without the linear combination coefficients needing to be 0. So this means that this is how the vectors look like. So we have one of the vectors that is indeed linearly independent of the other two, which is the third vector. So v3 is this one. But v1 and v2, they are linearly dependent on each other. Yeah, that's why we got this result that a3 has to be 0, but we can have a linear combination of v1 and v2, and we can still get to the origin, to 0. So, in conclusion, so this was only an example, but it was not needed. It was just to convince you. But the conclusion is that there is a solution to this system up here, which means that the vectors are linearly dependent. Yeah. And now, actually knowing this, knowing that vectors 1 and 2 are linearly dependent, if you actually look, one of them is 0, minus 1, 1, and the other was 0, 1, minus 1. Obviously, they are the same vector, but in opposite directions. They were parallel. That's why they are not linearly independent. So everything checks out. So you can see that the way of knowing if two vectors are linearly independent or not is to try to solve this equation over here. Okay? So that's the most important equation for this video. So I did two problems, two examples, but in the booklet of notes and problems, you have an example for each of these cases. So you have the example that we did, that was this case. You have an example in which the three vectors are inside a plane, but none of them is parallel to each other. Then you have an example in which the three vectors are parallel in the same line. And finally, the example that we did in which two vectors are parallel and a third vector is not. So you have how the solutions look like in each case. So go and have a look and make sure you understand, and you would be able to identify those cases.